Good afternoon, everyone. Thank you all so much for coming. It's really exciting to be able to welcome you to the Wetterhahn Symposium in person. Given the ever-changing state of things, we were worried for a while that we might not be able to convene the event in person. Even more exciting, this is Dartmouth's 30th Annual Undergraduate Research Symposium, which was named in memory of Katherine Wetterhahn after her passing. I know some of you were able to attend another Wetterhahn Symposium this weekend, hosted by the Chemistry Department, which celebrated Professor Wetterhahn's life and impact in the sciences. I hope that today's keynote address, delivered by another distinguished woman in science, and the poster session that follows will complement the discourses from this weekend. I'm really excited to get to the address, but I have a couple of quick notes. After the talk, we'll have time for a few questions for Professor Mirica, followed by the student award announcements. Now, I'd like to welcome another female scientist to introduce our keynote speaker. She's a molecular and cellular biologist, the Paul M. Doughton Jr. Professor of Biological Sciences, the Dean of Faculty for the Arts and Sciences, and someone I have had the great pleasure of working with for several years. Please welcome Dean Elizabeth Smith.
Well, good afternoon, and thank you, Morgan. It's really wonderful to see you all here today. As Morgan said, it's been a couple of years since we've been able to hold this poster session in person, and so it's just really an amazing opportunity. And on such a beautiful day, getting you inside to talk about science, I know is probably a little bit challenging, but I'm glad you're all here. So the symposium is an opportunity to celebrate the accomplishments of our undergraduate researchers who, like many, have overcome great challenges during the past 2 years in their pursuit of scientific inquiry. Whether a graduating senior or a first-year student joining a laboratory for the very first time, each of you has made their own scholarly journey, and I congratulate you on your achievements. I would also like to recognize the hard work and dedication of their mentors. These professors, postdoctoral students, graduate lab members offer our undergraduate students guidance, support, and constructive feedback. They really are indispensable for Dartmouth's rich undergraduate research experience. Now, I'm especially pleased to introduce to you our keynote speaker, Associate Professor of Chemistry, Katherine Mirica. Last year's recipient of the Karen E. Wetterhahn Memorial Award for Distinguished Creative or Scholarly Achievement. Professor Mirica came to campus in 2015 after completing a 4-year postdoctoral fellowship at MIT in the laboratory of Professor Timothy Swager. Prior to that, she received her PhD from Harvard University in 2011. A molecular chemist, Professor Mirica has made fundamental and exceptional advances in 3 areas: chemical sensing, adhesives, and energy storage, applying groundbreaking techniques in material science and organic chemistry to address global issues in healthcare and the environment. She is among the leading scientists worldwide in the emerging subfield of chemical sensors. Her current laboratory, the Mirica Group, is pursuing, among other things, pioneering research in the development of portable electronic carbon-based chemical sensors for the detection of hazardous gases and vapors. Their work has been funded by the National Science Foundation, the Army Research Office, the Alfred P. Sloan Foundation, the National Institutes of Health, Innovators Research Award, and other elite supporters of science research. Since arriving at Dartmouth in 2015, Professor Mirica has published numerous influential papers, including 6 in the top journal in her field, the Journal of the American Chemical Society. In addition, since coming to the college, she has filed for 7 patents as an individual investigator and signaling that her discoveries have the potential for significant impact. An exceptional teacher, mentor, and role model, Professor Mirica shines in teaching the advanced as well as the introductory courses in chemistry. She's guided the academic and professional progress of more than 40 undergraduates, 10 PhD students, 4 postdoctoral fellows, and even students from local high schools since joining our community. She's been especially active and dedicated supporter of the Women in Science Project, mentoring 9 undergraduate WISP interns to date. Please join me in welcoming this formidable scholar-teacher.
Wow, thank you, Elizabeth, for that very nice introduction. I hope to kind of live up to the introductory material. Today, I have an absolute pleasure to share with you some of the work that my group has been doing since we've come to Dartmouth in 2015 on the topic of materials chemistry, focused specifically in chemical sensing. It's really an honor to be here, and I really appreciate this opportunity to share the science with you. So before we get started, special shout out to Chem 6 students. Can you guys raise your hand? Those of you taking a class with me, woo! Good to see you guys. Awesome, and I'm looking forward to the posters afterwards as well. So I want to start with just a brief overview of what my group does. We work across a range of length scales in materials, ranging from molecular solids to network solids to macroscopic functional devices. And in all these realms of materials, we look to obtain an emergent function that is greater than the sum of the molecular components that we put into the system. And with that goal in mind, we have three major areas. We have an area on new adhesives development that we think can make an impact in the microelectronics industry. But by far the most central thrust for us is the area focused on sensor development, specifically multifunctional materials development for electroanalytical applications. And that'll be the topic of my talk today. We also apply some of these same materials that we develop, multifunctional materials, towards energy storage and environmental stewardship. And we do that primarily through collaborations, some of which are here on campus with the Thayer School of Engineering, but also with others at other universities. So today we'll just talk about one of these topics, focused on chemical sensing. And in the realm of chemical sensing, one of the goals in my group is to develop a platform technology for textile electronics that can make an impact in healthcare and personal protection and enable electronic acquisition of chemical information from a textile. We, in this area, aim to merge the portability of electronic devices that many of us have in our pockets today, here with us, with the ubiquitous nature of textile materials that we all wear, to create this chemical sensing platform technology using the textile substrate, where the textile itself will become an active component of a sensor. And because the textiles are so tightly woven into the fabric of our society, and also because the electronic devices are so ubiquitous now as part of our everyday life, we think that this idea of putting sensors into textiles can be a really scalable approach to chemical detection with the possibility of improving health, safety, and quality of life of people throughout the world. But while all of us gathered here today are dressed in textiles and also probably have an electronic device in our pockets, we don't yet have electronic textiles in our possession acquiring chemical information from our body. So why is that? I mean, there's a range of answers, but my take on that is that that is due to the lack of materials that have the features of being simple and robust enough to integrate into a textile substrate and actually hold up to the wearability of that substrate, but also lack of integration methods that are scalable of those materials into the textile itself. And so our work at Dartmouth in my group aims to bridge that gap by developing new stimuli-responsive materials, semiconductive materials that can integrate with the textiles, and also developing new methods of textile integration that can hopefully enable textile-based chemical sensing that can make an impact in healthcare in terms of disease diagnosis and monitoring of chronic diseases, and also in personal protection. So for example, multifunctional detection, filtration, and decontamination. And there has been tremendous progress in textile electronics already, but that has been primarily in the physical realm. So the majority of current electronic textile sensors are physical sensors, not chemical sensors. These physical sensors target physical properties and physical measurements such as heart rate, temperature, or strain. And these measurements don't necessarily require chemical innovation to achieve. They can rely on existing conductive materials that are integrated into textiles using traditional and existing textile integration techniques, such as sewing or embroidery or screen printing. And so, despite the progress in physical sensing that it has enabled these measurements of heart rate, strain, and so forth, the performance of electronic chemical sensors on textiles has lagged significantly behind. And I believe that is due to the lack of the right kinds of materials and due to also limitations of existing fiber integration strategies for chemical sensing materials. But there has definitely been progress, and it's important to acknowledge some of the progress that has occurred and the innovation in the device form factor that has enabled electronic chemical sensing textiles to sample analytes from sweat and determine things like pH, the concentration of the chloride ion, sodium ion, glucose, and oxygen. So some of the vital molecules that are important for biochemistry. But despite this progress, there's still several limitations for textile-based chemical sensors that really limit these types of analytical assays compared to a benchtop type of format. So when these types of sensors are integrated onto a textile, usually there's a diminishment in sensitivity and other performance metrics compared to a benchtop assay. And some of the problems that are responsible for that diminishment is lack of chemical precision. So the kind of materials that we use for sensing these types of analytes, which require modification to their surface with either small molecules or enzymes in order to achieve relevant performance metrics. Another limitation is the stability of interfaces. So once we put a sensing material onto a textile, for it to hold up to wear and tear of the textile substrate, it has to be exceptionally chemically robust, physically robust, and also respond in response to an analyte, but not many other things. So that stability of interfaces from a chemical and physical perspective of a material that's loaded onto a textile is still an issue. And then finally, these materials that are used for current chemical sensors on textiles lack multifunctionality. And what I mean by that is that they do one thing at a time. So they can sense, but they don't offer additional opportunities such as filtration or decontamination. And to achieve those additional opportunities, you'd have to load the textile with more materials. So my group aims to overcome this gap through design of new materials and new textile integration strategies. And we also have some specific goals in mind in terms of expanding the set of analytes for chemical sensing beyond the list that I showed, and specifically towards a list that includes molecules known as gasotransmitters. This is a class of 3 molecules: carbon monoxide, nitric oxide, and hydrogen sulfide. And 3 of these molecules are categorized in this class due to their biological importance. So for the longest time, they were believed to be just waste byproducts of metabolism, and also they're known to be chemically toxic. They're toxic upon inhalation, and their permissible exposure limits are listed here in the part per million range. But biologically, despite being or appearing as waste byproducts, these important molecules regulate a number of physiological functions, ranging from blood pressure regulation to immune response and possibly also learning and memory. And there isn't currently a single technology or a combination of technologies that can detect all 3 of these gases and differentiate them in living systems and enable understanding of diseases that these gases are correlated to in real time. And that challenge stems from their broad concentrations in biological systems, ranging from millimolar to nanomolar, and also their very short half-life in vivo. So from a biological perspective, being able to detect and differentiate these gases can enable deeper insight into a number of diseases that these gases are associated with. From a chemistry perspective also, because these gases are toxic by inhalation and constitute important environmental pollutants, being able to sense, filter, and decontaminate these gases is also important from an industrial perspective. So what we're developing is kind of a two-phase platform technology where we look to protect people from these gases and remove them from the environment, but also we look to make a platform technology that can enable important fundamental discoveries and understanding from a chemistry perspective in the biological systems. And for that, we have two parts to our technological development. We have materials development and then integration of these materials into devices. And one type of device that I will emphasize today is the textile substrate that can be viewed as a wearable, but it also can be viewed as a smart suture type of device, a smart bandage that can integrate with biological systems and enable new function. So in terms of our materials development, we take inspiration from biology. We don't try to mimic biological systems or hierarchical protein-based structures that biology has, but we are inspired by the molecular organization of proteins and specific organized molecular recognition subunits that are embedded within proteins and are capable of facilitating signal transduction and very good differentiation of these small reacting gases such as nitric oxide and carbon monoxide. And so in our materials chemistry research, we look to build materials that also have an organized hierarchical structure, but have embedded molecular recognition subunits directly within the material in order to bind to the analyte and facilitate the sensor response by changing the electrical properties of the material, such as work function, dielectric constant, or its conductivity. And because this class of materials that we work with is extremely modular, we have very good tunability and chemical precision in our molecular design to mimic, well, not mimic, but to be inspired by protein types of active sites, but embed them within a really stable material substrate. So the class of materials that we focus on are known as metal organic frameworks. These materials are composed of organic ligands, shown in gray here, and metal ions that bring the ligands together and interconnect them. And this interconnectedness creates a number of important properties in this class of materials that are very well suited for chemical sensing. So first, we have a chemically precise extended structure. We have a crystalline material with a periodic structure, and this surface is accessible through bottom-up self-assembly, meaning that the material can build itself when we can put the correct components into our reaction mixture. We also have extreme modularity. We can start with different building blocks. Imagine this as being a Lego type material. So by putting in different building blocks, but having specific chemical connections between those building blocks guide the material to self-assemble, we can tune the surface chemistry and the structure property relationships of these materials. And also, we have intrinsic conductivity of this material embedded within it through in-plane conjugation or delocalization of electrons through the plane of the material, and in the stacked structure that is a layered structure that tends to stack upon itself with multiple layers, we also can achieve conductivity through stack. So all of those are important features for electronic signal transduction, such that if something binds to the surface of that material, it will change its conductivity and we'll be able to detect it in a portable device. We also have, by design here, high surface area of this material, so a large exposed surface area, and that's really good for promoting chemical interactions with the analytes. We have high volumetric capacity for gas uptake, which is great because we're trying to sense gases. And that is a virtue of this material being porous, where the porosity is also built in by design from the design of the building blocks. And then the material is highly anisotropic, and that could be useful for tuning sensitivity and selectivity in the realm of sensing. And then finally, on the molecular level, we have some redox activity in this material, so oxidation, reduction types of events that can lead to reconfigurability of the surface. So lots of knobs to tune and dial in and obtain really unique multifunctional performance that we're really excited about. The nice thing is that these materials are extremely straightforward to make. Pretty much every student in my group who's come through this group at one point or another has made these framework materials. We can start with a commercially available hexahydroxytriphenylene and run a reaction that proceeds in water, under air, with some heat, in the presence of oxygen. So it's just like cooking. It doesn't really get more complicated than that for this particular material. And from those synthetic conditions, through a self-assembly process, we're able to obtain conductive and porous nanowires of the self-assembled framework material. I've never made these materials before I started here at Dartmouth. And when I did in 2015, kind of 2 weeks after we moved into the lab, one of my first students and high school students were able to run this reaction, and it works very well, very reproducible. So we're very excited about the involvement of undergraduates in this particular area of our research because the materials are so accessible. And in fact, we can take these nanowires and exfoliate them by sonication and obtain these transmission electron microscopy images that show the hexagonal porosity within the material as expected from its molecular structure. And that particular image was taken by an undergraduate who was a former WIST student and then went through the entire UGAR program at Dartmouth, Kennedy Jensen, who's currently at Geisel. Okay. So our focus is to merge this self-assembly process of the material building itself and also combine it with the integration step onto a textile substrate to achieve a textile-based chemical sensor. So in this particular example, what I'm showing is that we can take a cotton swatch and simply run the reaction in the presence of the cotton substrate under similar conditions with what I've shown, and get templated assembly of this material onto the cotton substrate such that we get conformal coating of the cellulose fibers by the metal organic framework crystallites. And this generates an electronic textile that has very good, robust performance, where its electronic properties are unperturbed by mechanical perturbations, which is good because we want a chemical sensor. We don't want a mechanical or strain sensor. Then what we do in terms of probing the sensing function of this type of electronic textile is apply voltage and measure current. And this constitutes one of the simplest chemical sensor types of devices, which is known as a chemoresistive device. So in this device, we hook up our material between two electrodes, and we apply voltage and measure current. So this is a constant voltage measurement that generates a current versus time plot. We then take that plot, deconvolute it, and basically normalize it to generate a sensing response. And the sensing response in the traces that I will show is basically proportional to the electronic resistance within the device. So when you're looking at these plots of negative delta G over G0, that's just think of it as resistance. So taking our electronic textile swatch and applying constant voltage and measuring current gives us the following responses to nitric oxide and hydrogen sulfide. I want to point out that from the concentration-dependent response, we can derive limits of detection, so we're able to detect these analytes at sub-part per million concentrations. The response itself for two different materials that we probed, two different frameworks that have the same metal but different heteroatomic crosslinks, the directionality of the response tells us something about the semiconductive properties of these materials. And by having an array of two materials enables us to differentiate these gases from each other and to deconvolute the array, the response of this array, and to begin to do some differentiation with some partial selectivity of each sensor to each analyte. So we're able to achieve sensing function, and we're able to maintain sensing function in the presence of humidity. So if we humidify our gas stream, we're able to still sense, which is good for practical applications down the road. But perhaps what's more unique about this particular sensing scheme is the ability not only to sense, but also to filter and decontaminate these toxic gases as they bind to the surface of the material that we're examining. So in this particular case, we've put two devices in series, and we just run the gas stream through that assembly. And the first device begins responding right away. That's the first trace that you see in the solid depiction on the plot. But the onset of the response to the second sensor is slowed down by the presence of the first. And this is because we have a dosimetric response, so the sensors don't recover. They act as dosimeters due to the fact that the gas is being taken up into this porous material and does not come through until some kind of breakthrough capacity has been reached. So from that, we can estimate an uptake capacity for these devices to be in the 10 to 20 millimoles per milligram of the material, and still maintain the limits of detection in the low part per million regime. While working on the project of textile integration, we've also serendipitously discovered another method for immobilizing framework materials on textiles. And this method involves solid conversion of pre-deposited copper metal into the framework material. And what turned out to be really interesting about this methodology is the beautiful orientation of the framework crystallites with respect to the cellulose fibers, which is templated by this reaction and the pre-deposition of copper. We did not, this was not by design. This was an accidental discovery in the laboratory by one of my first graduate students, Michael Coe, who has simply observed this reaction as he was trying to work with copper-based electrodes. But since this discovery and further investigation, we have noticed some really unique features of this particular deposition method or device integration method, one of which is patterning. So we can pre-pattern a pattern of copper on a textile and then convert it with very good fidelity to the pattern of our metal organic framework. So that's useful for potentially patterning materials and devices. We also can extend this method to a range of different substrates. So it's not limited to cellulose-based cotton, but can also work on silk, nylon, polyester, and paper. And this combination of materials together gives us a range of opportunities with which to pursue applications for these devices that can range between technical clothing development to low-cost diagnostics on paper, which is extremely inexpensive, to smart personal protective equipment on natural fabrics and synthetic fabrics, smart sutures, smart bandages, and smart filtration membranes. So it's a pretty broad potential applicability, and we're still trying to zero in on what are the best applications to develop. But the patterning ability is quite remarkable and extends well beyond a millimeter scale onto a micrometer scale. And we're actually quite puzzled by this chemistry, and for a while could not quite figure out the mechanistic underpinnings of this chemistry. But actually, after walking around on campus kind of every day and looking at the Baker-Berry library, we have realized that the type of chemistry that we're undergoing on this textile substrate during the restructuring process is very much analogous to the type of chemistry that the Baker-Berry library roof is undergoing currently. So here I'm showing a picture from 2015 when I started. This is right before the Baker-Berry library roof got replaced. And it was originally put in place when the building was built, and it was there for quite some time, holding up to the weather. But copper ages, it undergoes an oxidation process, and there's some underlying chemistry that is responsible for this malachite green color that we see on the copper roofs. And that color comes from a mixture of 3 different minerals, malachite, azurite, and brachytite, and all of them are basically just copper containing compounds, copper carbonates, hydroxides, or copper sulfates that form over time during the weathering of copper-based roofs. So I was very fortunate to start when I started in 2015 and witness the malachite green color of the copper roof on Baker-Berry. In 2016, there was a replacement of the roof, and we got this new shiny copper roof that looked just like copper metal. In 2016, this is shortly after the homecoming weekend, sort of in November timeframe, when it was still copper colored. So I've been keeping an eye on this ever since. And tracking it. I wish I could get and do some experiments on a part of the roof, but that's okay. So in 2017, we have gone into a copper, actually 2016, kind of 2017, after a few months of that transition, we've gone into a copper oxide phase, but there's a number of copper oxides that exist. So the first oxidation process, a copper 2 oxide, so it's a +1 copper oxidation state, and then further oxidation processes go on, and the material settles into the copper oxide, so CuO or CuS. S, depending on how much pollution and sulfur is in the area. We have excellent air quality in Hanover, so this aging process might take some time. So based on just my reading of what might be expected for us to fully age into the malachite green color and the air quality in Hanover, I would predict that by the 20th reunion of class of 2025, we might see the green roof. But I guess when you do come back for your reunions, keep an eye on the roof because it does monitor the passage of time in a very unique way. Okay, so we think our chemistry is analogous to the type of chemistry that's going on the Baker-Berry library, where on the Baker-Berry library we're intercepting copper oxides with sulfates, so sulfur-containing species to obtain sulfates, and carbonates with carbon dioxide that ultimately settle into these green-colored minerals. On our substrate, we have a much faster event. We don't have to wait for decades for this to happen, but it's still a copper oxidation process. In the presence of oxygen, we can oxidize copper. We also have a ligand, that organic portion of the framework that is redox active, that needs to undergo a redox event. Oxygen is absolutely critical to that entire process. If we take oxygen out, this does not work. And then once our partners are appropriately oxidized, coordination event occurs, and because of high effective concentration of copper metal at the surface of cotton, we're able to deposit the framework material onto the textile. And the kinetics works out beautifully to retain and maintain the patterning feasibility. So these materials still do chemical sensing. They are able to detect nitric oxide and hydrogen sulfide at part per million concentrations, similar to what we already established. But with some spectroscopic insight, we're also able to discern that not only we're sensing these materials, but that we are chemically converting them into less toxic and less volatile products. So in the case of hydrogen sulfide, we're actually trapping it within the framework as sulfur 0 or copper sulfide species. In the case of nitric oxide, and we determine this by a combination of X-ray crystallography, X-ray photoelectron spectroscopy, and diffuse reflectance IR spectroscopy. In the case of nitric oxide, we're actually oxidizing it to nitrate and other similar compounds, nitrite. We also get direct binding of the nitric oxide to the copper metal. And we can completely restore the framework material by washing it after it's exposed to these analytes. And not only we can restore it, we can actually perform washing cycles and maintain sensing ability by washing this material with detergent, water, bleach, and the sensing ability holds up, although it does begin to decay after multiple bleach washes. This material is also extremely stable to heat and abrasion, so this combination of this particularly stable sensing material and the textile substrates together make this a really unique technology. So far I told you about just one sensing material, and I want to give you just a brief glimpse into another sensing material. And in this particular case, going beyond the triphenylene framework that we talked about and utilizing a more complex ligand based on metallothiocyanine to achieve enhanced function. So making this metallothiocyanine, the framework containing material, is similar to what we talked about in triphenylene-based materials, except that the ligand itself has to be synthesized. But by utilizing solvothermal synthesis, we're able to achieve a crystalline material that exhibits particle-like morphology and also can be exfoliated into thin sheets. Placing this material into chemical sensors, we're able to achieve now much lower detection limits. And we attribute these detection limits in the part per billion regime for hydrogen sulfide and nitric oxide to the unique structure and the bimetallic system that we're employing, so to the molecular design of the material itself. This material also senses in the presence of humidity, and then making arrays of structurally analogous materials allows us to achieve differentiation of gases from each other in this arrayed format. We've also made another analog of this type of framework material instead of a metal organic framework, using a covalent linkage between phthalocyanine moieties to probe structure-function relationships and the specific role of the metals within the framework. So making this covalent organic framework required a significant amount of effort on the synthesis of precursors, but once we got that, with the leadership of one of the fantastic postdocs in my group, we were able to synthesize this covalent organic framework. It was the first material of its kind, so we got to name it. So we named it for Dartmouth College, DC, and 8 for the 8 lucky number of substituents on the periphery of our molecular precursor. So COF DC8 is a named material after Dartmouth, and we're particularly excited about that. It's also a crystalline material. We can characterize it. It's extremely robust. So compared to the metal organic frameworks that I talked about, which are already very chemically and physically robust, this particular material maintains its structure in the presence of concentrated acid and concentrated base, and does not decompose until 500 degrees Celsius. So it's very chemically robust, owing that robustness to the chemical structure that we employ. In terms of sensing, we take a little bit of a hit for hydrogen sulfide, but we maintain sensitivity to nitric oxide. And so what that structure-property relationship analysis tells us is that the presence of metallic nodes, specifically that are copper-based nodes, is really important for obtaining good limits of detection for hydrogen sulfide, while for nitric oxide, the nickel-based framework does the job. So we can glean structure-function correlations by studying structurally analogous materials. And from this entire class of materials, we think that their multifunctionality and their ability to be compatible with textile substrates has good potential impact for healthcare applications, personal protection, such as smart personal protective equipment, and potential for global scalability due to the accessibility of some of these materials based on earth-abundant elements. And I think there's a lot of creativity that can come from the development, materials development in this realm, where designing new and different framework materials that can be synthesized in a very modular, bottom-up fashion can facilitate new and exciting applications of these materials in a realm of different device architectures beyond sensors. And those device architectures can span energy-related devices, catalytic systems, spintronic types of devices, and go well beyond the sensing applications that I just highlighted today. So with that, I want to conclude by thanking my fantastic group. They're really a great group of people to work with, and I'm very grateful for their willingness to do new things with me. I also want to thank the sources of funding that have supported our research over the years, and I want to thank you for your attention, and thank you for this opportunity.
Can you guys hear me okay? Yeah. All right. I think we have just a few minutes if we have a question or two for Professor Mirica.
I have an observation, having been around for a while and watched our roofs slowly change color over the years. I think we're remote sensing the fact that we don't get the same acid rain we used to, because it's taking a lot longer to change green than they used to, I think.
Yes, acid rain will speed that up significantly. and I hope it doesn't. I think it's also kind of a litmus test to our environmental and air quality of how fast the roof will age. And I think right now it's pretty good compared to like major cities of where these patina roofs exist. Yeah.
It didn't used to stay in the black phase for very long. It seems to be much longer right now.
Interesting. I'll have to keep an eye on that. I hope that I'm fortunate enough to kind of see it through, you know, to the green phase.
Any other questions?
I was wondering about the biodegradability of these fabrics in the end and the green chemistry aspects of it. I wonder if you could say something about that.
Yeah, so the question is about the biodegradability and green chemistry aspect of it. That is a great question. We haven't looked at biodegradability explicitly yet. We're just starting to interface these materials with solutions of proteins and also beginning to look at biocompatibility with living systems. What we do know is that when we place these metal organic frameworks on textiles into water, we don't get any significant leaching out of the copper from the textile when it's just in an aqueous solution. Now, adding things to it will certainly change things, and we have yet to really analyze that.
One last question.
The copper organic high fidelity patterning that you mentioned sounds a lot like atomic layer deposition. Have you considered applications for micromachining and MEMS and that kind of thing?
We've thought about it, yeah. So micromechanical systems and things like that, and patterning of this substrate into some kind of micron sized spaces, I think remains kind of to be done. We haven't done it at that level. We've done this deposition primarily on the porous substrates, and we've actually encountered some difficulty with maintaining the deposition of the framework when copper on a planar substrate, such as glass or just non-porous polymer, is restructured into the framework. So we think that there's kind of a contribution from the mechanical anchoring of the framework to the textile itself that happens during that growth phase, and we have yet to get it to work well on a planar substrate, which I think would be critical to what you're suggesting.
You might want to look at the lattice constant of the substrate.
Yeah, that's a great point. Thank you.
Great. Well, thank you again, and if we could all thank Katherine for
Thank you.
sharing her work.
It's so fun to be here in person.
So before we release you to the poster session, we're coming up on our awards portion of the event. So just over the next few minutes, I'd like to call Professor Dean Wilcox, who is the president of the Dartmouth chapter of the sigmaseye Society, up to announce the winners of the Christopher Reed Science Competition.
Thank you, Morgan. I guess I should start off with just a little anecdote. One of the senior chemistry majors received an email earlier this week that said he'd been nominated into Phi Beta Kappa. And he thought it was spam because he didn't know what Phi Beta Kappa was. Of course, you all know what Phi Beta Kappa means. So just a word or two about what is sigmaseye. You don't see it over on Webster Avenue, do you? No? Okay. So sigmaseye is the Scientific Research Honor Society. It's the world's largest multidisciplinary honor society for scientists and engineers. It has a mission to enhance the health of research enterprise, foster integrity in science and engineering, and promote public understanding of science for the purpose of improving the human condition. And Lord, we need a lot more of that right now. sigmaseye chapters can be found around at colleges and universities around the world, at government laboratories, and more than 200 Nobel Prize winners are members of sigmaseye. So Dartmouth has a chapter of sigmaseye. It's not the oldest. It was actually founded in 1886 by Cornell engineering students and faculty. But it is an active chapter, and we actually do two activities. First of all is as an honor society, you nominate members for their recognition of their accomplishments. And there's 2 levels of membership: associate membership for young scientists and full membership for established scientists. And the local chapter also sponsors the Christopher Reed Science Competition. This competition is for seniors that do an honors thesis in science. And it's named after the late professor in the biology department, Christopher Reed, who was active in the chapter for many years. And we do this in partnership with WISP, and we're grateful for this opportunity to have a poster competition for these senior honors theses. And I'd like to call up Will Levitt and Brendan Keller to help with the announcement of the awards and passing out the prize. And Tim Smith. So these are three of the 5 judges that were here for the judging of the competition. Timothy Smith from the physics department, Brendan Keller from Earth Sciences, and Will Levitt from Earth Sciences. And I'm going to give Tim, you'll pass out the 3rd place prizes, and Brendan the 2nd place, and Will the 1st place prize. Okay, so you know, science is all about quantifying things, and so numbers are very important. And when you talk about prizes, you usually think about the 1st, 2nd, and 3rd. But we were so amazed this year, as we are every year, at the quality of the presentations, the quality of the work. Just amazing. It's just almost overwhelming. And it's really hard to decide on the number of winners when there is so much outstanding scientific research that takes place here at Dartmouth among our undergraduate students. And so without further ado, we're going to announce the winners of this year's Christopher Reed Science Competition. Because it's 3rd place, we have to have 3 3rd place prizes. Just because we can't decide. So one of the 3rd place winners did research with the title Systemic mRNA Indicators of Glioblastoma Progression. Advisor was Artie Gur, Peter Chabot. Is Peter here? All right, and the ribbon you should put on your poster, okay? Not on your chest, on your poster. All right. The 2nd 3rd place prize was research entitled Hamiltonian Engineering of Dipolar Coupled Spin Systems Using Reinforcement Learning. Advisor was Chandrasekhar Ramanathan. The winner was Owen Eskandari. All right, the 3rd place prize was research entitled Validating a Mouse Model to Examine Brain Permeant NLRP3 Inhibitors. Advisor was Matthew Varda, Bryn Rankin.
The advisor for the was Tristan.
What's your pardon?
The advisor for this one was a different name.
Last minute change in the schedule here.
Not changing the winner.
Not changing the winner, changing the advisor. Okay. So the first of our 2nd place prizes was for research entitled Barium in Seawater, Global Distribution, Relationship to Silicate and Barate Saturation State. The advisor was Tristan Horner, and the winner is Okiomete. Credit where credit is due, exactly. All right, the second place prize for research entitled TOR-SH, Obfuscating Consumer Internet of Things Traffic with a Collaborative Smart Router Network. Advisor was David Coates, the winner's Adam Vendenbouche. So 1st place prize, there is 1 winner. The winner did research entitled rotating a permanent magnet to improve the precision of magnetic drug targeting. Advisor was Jack Hoops. The winner is Charlie Reeder. And before we end, I'd like to point out that all the participants in the Christopher Reed Science Competition will be nominated by the chapter for associate membership in sigmaseye.
Thank you very much, Dean. Appreciate it. Well done, everybody. Next up, announcing for the Award for Library Research in the Sciences, I'm happy to bring up Jane Quigley, who is the Head of Research and Learning for STEM, Business, and Economics at Dartmouth Library. Thanks, Jane.
All right. Hello. Good afternoon. I'm Jane Quigley, as Morgan said, head of the library's research and learning programs for STEM, business, and economics. This year, the Dartmouth College Library presents the 7th Annual Library Award for Research in the Sciences. These awards are sponsored by the Friends of the Dartmouth College Library, and they recognize students that demonstrate an exceptional ability to conduct research in the literature of their field, and who have developed an outstanding pattern of research and inquiry. This year we have 2 winners who will each receive $250 and a Certificate of Achievement from the library, and I'm pleased to announce their names now. If that person is present, I would like it if they will come up in person to receive the certificate and award letter. As I read out their award, the check is in the mail. The first recipient of the 2022 Award for Library Research and Science goes to Virgil Alfred, class of 2022, for his research on the honors thesis, Where Do Channels Begin? In recreating, Virgil, are you here? Yes, all right. Congratulations. I'll take the sticky note off it. There you are. In recreating the research from an important 1988 article in the journal Nature, Virgil addresses the very important topic of reproducibility in scientific research. His submission showed his growth as a researcher, adept use of the library catalog, and citation management tools throughout his research process. Please stop by and see the results of his research on his symposium poster, which is titled Predicting and Determining Channel Headwater Locations and Initiation Thresholds. The second recipient of the 2022 Award for Library Research in the Sciences goes to Akia Watts, class of 22, for her research on her honors thesis. Akia, are you here? Akia explored the intersection of African American vernacular English and colorism in the perception of African Americans in professional and social settings. Her interdisciplinary research involved consulting with 2 subject librarians with expertise in different research areas, and the use of a number of specialized sources. Her submission showed her growth as a researcher and the development of advanced search skills. You can see the results of her research on her symposium poster titled Interaction Between AAVE and Colorism in Attitudinal Judgments of African Americans. So for their accomplishments, each student has received a certificate and an award of $250. Please join me in congratulating Virgil and Akia.
Thank you very much. All right, home stretch. We have one more set of awards to give out, and I'm really happy because these are the WISP Sophomore Scholarships. There are 2 awards that enable highly motivated and deserving WISP interns to continue to do their research from freshman year into their sophomore year with their faculty mentors. It was really difficult to make this selection. We had an unusually large and not unusually, but very talented pool of candidates who applied for these scholarships, and it was a really difficult selection to make. So the first of these awards is the Barbara E. Crute Memorial Internship, which is named in memory of Dr. Barbara E. Crute, a former Dartmouth biology researcher and a committed WISP mentor. I'm happy to say that this year's Crute Award is going to another burgeoning biologist, a young woman who exudes a love of research and laboratory science. Devin Tullio, are you here? Any Devin? Hi, Devin. Fantastic. Congratulations. The second of the sophomore scholarships, the Carol Folt Research Award, honors the dedication and significant contributions of Professor Carol Folt to WISP, to the Dartmouth community, and to the sciences as a whole. Carol was one of WISP's co-founders and one of the original faculty mentors of WISP, and has served as the Dean of Graduate Studies, the Dean of Faculty, Provost, and Interim President at Dartmouth. Most of you know Carol, if you've been here any amount of time. I think she would be really pleased to know that the award named in her honor is going to a young scientist who has shown an extreme aptitude for learning quickly and engaging in scholarly inquiry. Lauren Kayari, who has worked with Professor Meredith Calley, could you please come up? And then as a bonus award, we do actually have one more award to hand out because we just couldn't make the decision this year. We have one award to recognize the talents and achievements of one WISP intern who has dedicated herself to research and pursuing science opportunities wherever she sees them. I was particularly struck by the strong rapport she built with her faculty and postdoc mentors. Katherine Mirica, I'm really pleased to say that you've been awarded the WISP Research Engagement Award. So if you're here and you'd like to come up. Hi, Katherine. Great, and that concludes our awards ceremony. So once again, I'd like to thank you all for coming to the keynote address, and if you would please give a hand to Professor Mirica for giving us that excellent talk. And I hope you all enjoy the poster session. Thank you.